Okay, let's get started. Let me share the content. Okay, can you see the slides? Yes, okay, good. So we're gonna move on to the first process that we will work on the silicon wafers when the wafers are all ready. So thermal oxidation is gonna be the first one that we're gonna learn, right? There are many more coming after this. Before we proceed, let's recap on a few things that we've learned in um, during our last lecture. So basically on clean room. So let's give some recap. What is a clean room? How would you define, how would you summarize a clean room? Okay, what is clean room? Control environment. Okay, good. Apa lagi keywords around clean room? If you have to define what is clean room, control environment. Yes, good. Low level of pollutants. All right. If you have to say like two sentences maybe, then what are other keywords? A space with controlled environment with low level of pollutants. What are the examples of parameters do we control? Contamination. What else? What else do we control in a clean room? What has to be fixed? Cleanliness, air cleanliness, which reflects number of particles per meter cube, if you like. Okay, what else? Apa lagi yang kita control dalam clean room? Cleanliness, pressure, very good. Okay, what else? What are the typical one in a space that we normally control? Pressure, cleanliness. Apa lagi dua parameter yang penting yang kita selalu control. Even in the lab kita control juga parameter ni. T and H. Apa T and H? T and H. What are those two? Apa T and H? Yes, temperature and humidity. Okay. Yeah, good. T and H. Temperature and humidity. So those are among the parameters that we control in in a clean room. So describe classification of a clean room according to the standard. So if you have to tell me what is the cleanest clean room, what is the class? What class would you say is the cleanest? Kelas apa yang paling bersih? Clean room definition. Kita ada ISO on one hand and the other hand we have the class. Kelas apa yang paling bersih? Is it 100, 1000, 10,000? Kelas apa yang paling bersih? Is the higher better or lower better in terms of the, yes, class number, class 1, good. So class 1 is the cleanest, okay? So you have to know for each class that we use as a classification, what sort of number of particles that we control in each class, right? Per meter cube. Okay, go on to the third one. What are the potential sources of contamination in a clean room? Right? What contributes to contamination in a clean room? Give me the first one, the easiest one. People, yes, people. Around 75%, right? So what comes from people? So apa yang kita contribute to the contamination? How? Let's pinpoint the sources from us, human. How do we contribute to contamination? I'll give you examples. Skin, hair, yes, very good. Lagi, apa lagi yang saya cakap is a big no-no tu in a clean room? It's a big no-no that you can, yes, makeup, right? Makeup boleh jadi particles, oil, grease, and everything. Hair, skin, sweat, in fact. Okay, selain human, what else? What are other potential sources of contamination? Ventilation, yes, ventilation. So it'll be a source of contamination if your filters are not working fine or the filters are not replaced when the time is due. There's no PM done on the filter, or the quality of the filters that we use for our HEPA or ALPA are not good enough. Ventilation, yep. What else? Give me one more, then we move on. Yep. Equipment, room structure, yes. Right? Equipment, we have moving parts. Some could be exposed. Room structure as well. If the flow is not correct, if you are having a turbulent flow, then we're gonna end up with contamination as well. Okay, we're gonna uh, heat the particles that could be on the floor for them to um, fly up higher again and contaminate your wafers and other stuff. Right. Done. Good contamination. So clean room is quite straightforward. So let's move on to our first process, thermal oxidation. So what is thermal oxidation? Thermal oxidation is basically a process where we grow our oxide, a thin layer of oxide or a slightly thick layer of oxide, depends on the purpose of the oxide. So we grow the oxide by thermal process. So that's why we call it thermal oxidation. On the other hand, you can also have your oxide on your silicon wafers, for example, by deposition. Cumanya itu kita tak panggil thermal oxidation lah because it's by thin film deposition. So maybe some of you have done sputtering or evaporation, like E-beam evaporation last time during your FYP. So if you work on sputtering or evaporation, so these are called thin film deposition. So you actually deposit the layer, for example, oxide or nitride or carbide on silicon or on glass or on plastic, on whatever substrates. So these are called thin film depositions, which is not thermal oxidation. Thermal oxidation kita grow kan dia, bukan kita deposit. Deposit and grow are two different processes. Kita grow daripada parent substrate tu. So in this case it's silicon. So we grow silicon dioxide from the silicon. Kita akan tengok kenapa kita grow from the parent and how does it work, and what's the mechanism involved during the growth process of thermal SiO2, thermal oxidation. We're going to see later on. So thermal SiO2, it's usually used for gate ox or field ox. So gate ox is the gate oxide under the gate. If you look at this structure, you have polysilicon gate as your gate dekat center punya tu kan, center area tu. So below the gate we have oxide. So if you can recall your MOSFET structure, we typically have a gate, gate ox under the gate, and then we have source drain on the left and on the right, and we have body where it's made of silicon. So is the oxide is for the gate oxide. Okay, so On the other hand, the oxide can also be used as field oxide. If you look at the side there on the right hand side and on the left hand side, the field ox can be used for isolation between active devices, or in fact, it can also be used for isolation of active area and non-active areas. Okay, so in this case, you can see gate ox and field ox. So we want to grow by thermal oxidation a high quality oxide layer on a silicon substrate, because we're talking about IC fabrication. So you want your gate to be of high quality. And last time when we talk about MOSFET, we have discussed about, if you can recall, high K dielectric, because of the technology node going smaller, and the thickness of the oxide, particularly gate ox, is also shrinking. And if you're working with a very thin layer of gate ox, so we could be working with possibility of tunneling as well. So we don't want that to happen. If you design your your transistor to be off, you don't want it to be on when it's supposed to be off. So you want to avoid leakage unnecessarily. So that's why we need to grow a very high quality oxide layer under the gate. Okay, what are the properties of thermal oxide? Uh, there are a couple of properties that we need to know, the basic ones. First is it has to have excellent electrical insulation. So it has to be a very good insulator, because you want the oxide to work very well as a barrier. So despite the low thickness of the oxide in the device, so it's a bit challenging because you want it to be a good insulator, but you are also shrinking the thickness of the oxide to as low as possible. So it's a bit it's a bit counterproductive if you like, but we have to do it. Okay. High breakdown electrical field. It has to withstand high electric field from the high voltage application. So it's very difficult if you're talking about high bias and low thickness of the oxide, and yet you want it to have a very high breakdown electric field. Stable and reproducible SiO2 interface. You want your SiO2 to be very reproducible. So that means whenever you grow your oxide by the oxidation process, so kita kena measure the thickness of few spots on the wafer. So well, typically in the fab, if you have a 8-inch, for example, 8-inch 200 wafers, um, you might have to measure a couple of spots of oxide thickness on the wafer, at least I think 5, 9. Some even go beyond 10 points. So the more points you measure, the more accurate the data is, and you can see uniformity of the oxide growth across the silicon. But on the other hand, if you are looking at that particular measurement, there's always two things that you have to think about. One is the uniformity. So that means you want to measure as many as possible, but you also have to bear in mind that you have WPH, wafer per hour capacity, or throughput that you have to deliver. So that means if you measure more points, you're going to slow the process down. And if you measure less point, you don't see much in terms of uniformity. So it's a bit of a juggle between what do you want to see conclusively, and also the wafer per hour that you can deliver through your production process, right? So that's why we typically go with sufficient points, which are enough to give you the whole idea of uniformity and everything, but that wouldn't jeopardize your wafer per hour capacity. Right. The fourth one is conformal oxide growth on exposed silicon surface. You also want to have, if you look at the images down there, so if you have your oxide below silicon, then you have silicon there, silicon feature there, and in some cases you might also have to grow um, a conformal oxide on the square of silicon on the silicon feature. So it's quite challenging if you're working with such a feature, because you want to have conformal growth, and if the oxide is very thin, so you might be encountering problem particularly at the edge of the square yang dekat bucu tu. It's gonna be a bit challenging to get conformal there, and also to have your silicon oxide integrity at the edges there. Sebab bila you go 90 degrees like that, it's very hard to form a conformally, especially if you're talking about thin oxide. Kalau you go for thicker oxide, then it's okay because it's gonna be thick anyway. So kalau you ada problem dekat these edges, then it will just be covered more or less. But if you go for a very thin one, then you might be seeing defects on the edges. Okay. Next is SiO2 is a good diffusion mask for common dopants. So we have learned last time in 386 that you want to dope the surface, but then there are occasions, or there are events, for example, like in MOSFET, where you don't have to dope your whole surface blanket. Maksudnya kita tak nak dope the whole surface lah, kita nak dope in selective areas only. So at that point, the thermal SiO2 will be a good diffusion mask. So what it does is you want to grow your oxide. Then you want to maintain your oxide on selective areas that you want to block the dopants from coming in. We'll see how to do that in lithography later on, and in etching process as well. So first kita akan grow oxide blanket, and then you need to do some patterning of the oxide in order to define areas of oxide that you want to keep and other areas of oxide that you want to remove. So for the areas that you remove, area yang tak ada oxide, kalau you tengok dekat sini ya, you tengok dekat gambar yang atas ni, oxide yang exposed, oxide yang remove, where you can see the silicon, the dopants will be coming into the silicon from that opening. So areas yang you ada oxide, you akan block dopants from coming in. So if the oxide is thick enough, so it will be able to block the dopants from coming in and dope the underlying silicon. So kalau you nak guna silicon oxide as a mask, you need to have a good integrity oxide with sufficient thickness. Kalau you punya oxide yang you pattern you ada kat situ tu is not of sufficient thickness, is no point, because the dopants are going to come in anyway and dope the underlying layer. So you will end up having the whole surface dope, even though you have oxide on certain areas, right? You don't want that to happen. So we'll see later on what is the sufficient thickness of oxide that's required for it to be a good mask against different dopants. Okay, we're going to see later on. Next one, next property is very good etching selectivity between silicon and silicon dioxide. We're going to see later on, you might want to pattern certain areas of oxide, and then you need to do some etching using HF, because HF is going to eat or etch the SiO2 from the surface. so it has to have a good selectivity on the surface. So if you don't have a good selectivity on the surface, that oxide, so if you go for an HF dip for a brief duration, so you might not be able to completely remove the silicon oxide from the surface, right? 7 is an amorphous material. So silicon dioxide, in this case, if you grow by thermal oxidation, is typically an amorphous material. Okay, all right. So what process do we do to get the thermal oxide? So how do we actually do the growth? So if you talk about thermal oxidation process, we have the first one is called wet oxidation, and the second one is called dry oxidation. So you can grow your oxide either by wet process or by dry process. The first one, if you look at thermal oxidation techniques down there, the wet process involve water vapor. Water vapor. So you can see the reaction in the on the slide there. Silicon is your silicon wafer plus your H2O. H2O is the water vapor. So you need to vaporize the water that you use, and then it will be turned into vapor, and then the vapor will be sent by incoming gas to the surface of silicon, and then the thermal oxidation process takes place. So you're going to end up with silicon dioxide as a solid. So that means your silicon, if you look at a cross section, silicon is now wrapped with with oxide. Okay, so plus hydrogen as the byproduct. On the other hand, the second process is called dry oxidation, where you don't use any water vapor at all, but you put your silicon into furnace, and then you turn on incoming oxygen gas to do the oxidation. So there's no water vapor, but there's just O2 gas for the oxidation to take place. So you're going to end up with SiO2 solid, and there's no byproduct. So there are two options that you can do, either wet or dry. We'll see what's the difference between wet and dry, and what are the pros and cons of wet and dry processes. So, okay, um, so this particular process is thermal oxidation. So let's look at the configuration of the process. So heat is added to the oxidation tube during reaction between oxidants and silicon. So the oxidants here can be the water vapor from a wet oxidation process, or the oxygen gas itself from the dry oxidation process that will be reacting with silicon to produce SiO2. The typical temperatures for this process is roughly 900 to 1200. It depends on what sort of thickness do you want, and how long do you need, or how long do you have um, to be able to get that thickness. So the higher temperature that you go, uh, the higher is the growth rate. So you're going to end up with thicker oxide in a shorter time. Um, Oxide growth rate increases as a result of the heat. So yep, if you give more heat or higher temperature, if you like, so you're going to end up with higher growth rate, or you give longer time for the growth, so you can end up with a thicker oxide as well. So this is one of the examples of the process. So if you imagine this configuration, or you have a furnace, you have dry oxygen gas there, O2, so you can turn it on into the furnace to do the oxidation. Any of you have done any oxidation process in your FYP? Ada yang buat FYP oxidation? Growth? Ada tak? Or anyone work with SiO2 at all? No? No one? Ada pernah buat any oxidation process? No. Alright. Okay, that's fine. So, yeah, this is what are the details of the process. Wafers are placed in a wafer load station, if you like, the wafer holder there. So it's typically placed vertical. So you have a batch of silicon placed on quartz board. So dia punya holder tu, we call it quartz board. So it can stand high temperatures. So up to 1000 plus, and the typical process temperature is 1000 below. So it can stand high temperatures. So they are usually whole vertical. So some process might horizontal as well. So there are pros and cons to the horizontal and vertical furnace structure. Dry oxygen is introduced into the chamber. So if you use dry oxygen, is it wet or dry process? Kalau you pakai dry oxygen, kalau you pakai oxygen gas, is it dry or wet process? Dry kan, straightforward. Kalau you pakai oxygen gas, then it's a dry process. If you use water vapor, then it's a wet process. So to be able to get that water vapor, you akan pakai water, and then you will place the water in a bubbler, so dia akan bubble at some temperature, and they can produce water vapor. So dry nitrogen is introduced into the chamber. Nitrogen prevents oxidation from occurring. So yes, you purge the chamber with nitrogen first because you don't want to have oxidation where you don't want to have oxidation. So maknanya proses itu kita control, particularly if you have your oxygen as your oxidant. So you don't want the ambient to contribute to the oxidation. So ambient is partly oxygen as well. Kalau you biar dalam ambient atmosphere pun, it would oxidize as well. So maksudnya tak semestinya you guna oxygen gas saja to be able to do oxidation. You can also use ambient because ambient is also oxygen. But kalau you pakai ambient, you cannot control lah because you don't know exactly what's the flow rate and everything because it's in the ambient. On the other hand, if you use dry oxygen, you can control the MFC, mass flow controller, to deliver certain flow rate that you want into the chamber for the oxidation to take place. So nitrogen is firstly purged into the chamber to prevent oxidation from occurring. You want the ambient to be with nitrogen first because you don't want to just start it without control. Then nitrogen gas flow shut off and oxygen is added to the chamber. Then the moment the chamber is filled with nitrogen, you then turn off nitrogen and turn on oxygen into the chamber, right? Occurs when furnace has reached maximum temperature. So for example, if you want to oxidize your silicon at 1000, so the moment the temperature has reached 1000, the temperature is ready, everything, the ambient is ready, then you turn off your oxygen, turn off your nitrogen, turn on your oxygen, and to fill the ambient with oxygen and to start the oxidation process. Oxygen can be in a dry gas or in a water vapor state. So it depends. If you want to run dry ox, then you will use oxygen gas as your oxidant. On the other hand, if you want to run wet ox, you will use the water bubbler to produce the water vapor and to start the oxidation process. So the moment the process is finished, for example, if you want to oxidize your silicon for like 45 minutes, for example, at 950 degrees C, then the moment you have done the process, so you have to stop the oxygen flow, reintroduce the nitrogen into the chamber to stop the oxidation process. So kalau you punya process to keep having oxygen, it will still oxidize because it will take some time for the temperature to ramp down. Kalau you run at 950, you don't want to keep the atmosphere at 950 already, because it's gonna keep oxidizing the silicon. So you want to reduce the temperature right away in certain profile, and you want to reintroduce the nitrogen so that the oxidation can be stopped. Okay, nitrogen gas reintroduced into the chamber stops the oxidation process, and then when the process is completed, wafers are removed from the furnace and inspected. Okay, inspected here means thickness needs to be checked and particles need to be checked as well. So typically thickness and particles. So you want to know how much thickness have you grown out of your dry or wet ox just now. And also you might want to know, you need to know as well, not might want to know, you need to know as well whether or not the process or the chamber that you use has introduced particles on the silicon wafers unnecessarily, right? So you might want to know the particle count before the process and after the process so that you can know how much is contributed by the process, if there is at all. Okay. So dry oxygen is the oxidant. So used to grow oxide less than 1000 angstrom thick or 100 nanometer thick. So, and it's a slow process. So if you look at the growth rate there, oxidation rate, so it's somewhere 14 to 25 nanometer per hour. So that's why we use dry ox. So dry ox is actually meant for thin oxide formation. So 14 to 25 nano per hour. So kalau nak grow like 10 nano or less, so you'll need a couple of minutes. Dry ox, okay, dry ox. So thin oxide, thin oxide grown less than 15 nano typically, even though you might say that less than 100 is also thin, but to put into perspective, if you talk about MOSFET, then 100 nano is not thin enough. So we're talking about below 10 here or below 15. For features smaller than 1 micron, because now if you talk about all the transistors that are trying to meet the Moore's law, conform to Moore's law, then we're talking about all sub 10 nanometer. So that means all below 10 nanometer technology node. So and they all use very thin oxide. Okay. So for MOS transistors, MOS gates, direct component, so there's no more 1 micron transistor untuk high-end application. Kalau if you go for the low-end applications, then maybe you're talking about microns. Okay, if you talk about technology nodes, Moore's law, high speed, and everything, micron is no longer in the equation. It's all sub 10 nanometer. Additional of chemical species to oxygen decreases oxide growth rate. So you need to, so you might need to include some species as well into the process, like ACl, TCE, TCA into the process. We'll see why later on. So decreasing pressure slows down oxide growth rate. So when you actually run the process, you can also modulate the pressure of the process. So if you go for a higher pressure, you're going to end up with thicker oxide within the same time, at the same temperature. If you go for a lower pressure, then you're going to end up with a thinner oxide within the same time at the same temperature. So you can also modulate the temperature, the pressure, the time. So these are the typical parameters that you can control to be able to get your desired oxide. Wet ox, on the other hand, 1135, wet ox, on the other hand, uses water vapor as your oxidant. So you have water as your precursor, and then it has to be vaporized by usually water bubbler. So it gives faster oxidation rate. So the growth rate is like 100 nano to 120 nano in an hour, in comparison to dry ox is now 14 to 25. So this one is like 100, so more or less 4 times higher than the dry ox process. But this one is relative. It depends on the pressure and some other stuff as well. But typically, this is the range. Preferred oxidation process for growth of thick oxide. So usually, if you want to grow thick oxide, so thick depends on your application. So it's very relative. In some application, 100 may be considered thin. In some other application, 100 nano may be considered thick. So when you say thick, it really depends on the application or your devices. But if you're talking about comparison between the growth rate of the two, 14 to 25 and 100 to 120 nano per hour, then normally we'll use wet ox for thick oxide. So in general, we normally use dry ox for our gate oxide and wet ox for our field oxide generally. Okay. Tapi kalau you punya field ox is thin and you need certain properties from the thin ox or from the field ox, you might as well go for dry ox. Cumanya you have to spend longer time to be able to get the same thickness. Okay. So function of oxide layers, apa function oxide layer yang kita selalu guna? Tadi kita dah cover dua proses untuk grow, either it's wet or dry, and don't be surprised that some processes might need a combination of two. So that means kalau you ada certain oxide that you need with certain characteristics or certain properties, so you might want to do dry and wet ox together in the process. Maksudnya, you might want to sandwich the whole oxide and actually break the oxide down into maybe, I don't know, 3 steps. So you might want to, for example, if you have silicon here, you might want to have your dry ox first, and then followed by wet ox, followed by dry ox, so that you have a very good oxide, higher quality oxide first, then lower quality in between, and then higher quality at the other end, so that you sort of sandwich the oxide within the whole bulk of oxide. So it can be done as well. So it's not necessarily one specific process for your process. So it can also be a mixture of dry and wet for certain requirement. Okay. So why do we use oxide layers? There are few function of oxide layers. The first one is preservation. So preservation kita dah belajar hari tu in your trade 6 when we learn about surface preservation in particular, where we need to preserve your dangling bonds or the surface with a very thin layer of oxide, or in fact can be done by amorphous silicon and some other layers as well. But for this particular material, silicon dioxide, it can be used for preservation as well. So physically protects the wafers from scratches, particle contamination, and this is more physical, like a wrapping macam you nak tutup dia lah, nak tutup. But on the other hand, electronically you can also preserve uh, the defects or the terminated layer or the surface in general from recombination. Traps mobile ion in oxide layers. We can also trap mobile ions. So we have discussed about the danger of mobile ion. It can kill your device instantly. So like what we've done in gathering last time, we've discussed few lectures back on gathering, where we do emitter diffusion or n-type diffusion by phosphorus, and then we induce migration of impurities into the layers, and eventually they are removed. So this is another another scope where the oxide can trap mobile ions in the oxide layer. So the oxide can also be used for masking purpose, not process. So yep, this one. So you have your silicon there in purple color, and then you want to dope your exposed area of silicon there in the blue layer, right, in the blue color. So you want to block your dopants from doping your surface by using the red layers. So the red layers belong to the oxide. So we'll learn how to grow the oxide later on. Blanket, the whole, bila saya sebut blanket means the whole surface, bukan selective area. The opposite is selective area. So you will learn later on how to grow the oxide blanket, either by wet or dry, or by combination of both. And then we'll also learn on how do we pattern the oxide. That means you want to keep the oxide on certain areas and remove the oxide from some other areas by lithography and etching later on. And then the moment the silicon there is exposed in the central region there, so you can go for a diffusion process, or in fact implantation process, to dope your dopants, either is for P dopant or for N dopants. It can be phosphorus, can be antimony, can be boron, can be arsenic, to be able to dope the exposed area, right? So the moment you finish with the doping process on the exposed area, you can then remove the oxide mask, the red layers, by just dipping this sample dalam gambar ni. You ambil sampel ni, you dip dalam HF, then you're gonna remove the oxide, because oxide dia akan makan, HF dia akan makan oxide, dia akan remove oxide, dia akan etch. Then you're gonna end up with just the two layers, the blue one and the purple one, and there's no more mask left. Then we can proceed with our subsequent processes, right? So you can use the oxide as a mask as well. You can also use your oxide as a mask for etching process if the etchant doesn't etch the oxide. So you can use to etch the open areas. Okay, boleh juga. Right, the third function is as insulating material. So we've learned about gate ox function last time when we talked about MOSFET. So particularly under the gate region, where you want to have a very thin layer of oxide, particularly below 5 nano for the modern devices, if you like. So it allows the inductive charge to pass between the gate and gate metal and silicon. So if you look back at the switching process of the MOSFET, you ingat tak kenapa kita panggil dia MOSFET? Metal oxide semiconductor field effect transistor. Do you still remember how do we induce the formation of the channel under the oxide? And we also did discuss about what if we don't have oxide. Still remember? Anyone who did MOSFET last time? Your presentation on MOSFET? Why do we need the oxide layer there? Can we don't have oxide? Can we don't have oxide? Fazira, can we not have oxide there for a MOSFET? Boleh, Fazira? Can you run without oxide? Ah, okay, unmute yourself and...
I don't remember, but I don't think we can.
Okay, any reason for that?
I don't know. I don't remember.
Okay, all right. How does the switching works in MOSFET? How does the switching work? Shazwani, can you recall the switching? How does the switching works? Ingat lagi ke how does the switching of MOSFET takes place? Shazwani? Hazika? Hazika still can recall? Why the oxide there? Don't remember? Anyone? Anyone else? Inas, ingat Inas? Siapa buat MOSFET last time? I couldn't remember myself. Can we run without oxide? Again. You go back and try to recall why do we have to have oxide? What if we don't have oxide? Can we not have oxide at all? Right? So the oxide is red in color under the gate. Okay, you want to have oxide down there for some reason. Yep, insulator, yes. So that means you said insulator, yes, it acts as an insulator. So if we don't have the insulator, if you don't have the oxide there, so what's going to happen to the operation of MOSFET? If you talk about N-channel enhancement MOSFET, enhancement and depletion, ingat lagi ya? What is enhancement versus depletion? What is the difference? Because it's going to be related to this subject anyway. Ingat tak? What is the enhancement and depletion? What's the difference between these two? That's why the 386 is a prerequisite for this subject. Kenapa enhancement? Still remember what is the obvious difference between enhancement and depletion? Mode. When you talk about enhancement and depletion, what does it reflect? What does it show actually? It shows the channel, right? Channel formation. So if it's due to the channel, then why in some cases it's enhancement? Why in some other cases it's depletion? Yeah. It's okay, I'll leave it to you to go back and check again. Sebab dia akan affect kita punya proses selepas ni. Whether it is enhancement or depletion. If you talk about IC fabrication, if you talk about MOSFET fabrication, so this enhancement or depletion is going to determine your process flow in the fab. Okay, why and how you figure out. Okay, the fourth role of the oxide layers, or the fourth function if you like, dielectric material, insulate between metal layers and field oxide. Well, it can also be used as an insulating layer between metals. If you talk about field oxide, if you have metal adjacent metal, if you like, neighboring metals or neighboring devices, neighboring active areas. So field ox, thick one, can be used to isolate the neighboring devices. Next, fifth one, tunneling oxide allows electron to pass through oxide without resistance. So in some cases, you might need to have tunneling oxide as well. So you want the carriers to tunnel through the oxide for some application. If you talk about solar cell, for example, that I can recall now, you can check on this TopCon silicon cell. Dia punya technology dia is called TopCon. TopCon. You can figure out why is it called TopCon and how does it work. So it is based on tunneling of carriers through oxide to be able to ensure device success. So without that, it wouldn't happen. Okay. So at that point, you want the carriers to tunnel through your oxide to be able to do the job. On the other hand, in some other devices, in some other cases, you don't want tunneling to happen because if you have tunneling unnecessarily, you cannot control your device operation. Particularly if you talk about on-off states of your transistors. But in some other devices, some other applications, some other contexts, you might want the tunneling to take place. So tunneling ni kita acknowledge dia as one of quantum mechanical effects at a very low thickness and under some condition in certain device, and you want to manipulate the tunneling to your need lah, to your need. Either you want it to happen or you don't want it to happen. And for that to take place, you need to know what do you need, what does it take to for the tunneling to happen, and what does it take for the tunneling to be avoided, to be prevented at all. So we acknowledge that tunneling takes place at a very low, quantum mechanical level. So use it for your own need. Okay, one more thing. I think let's go for this one and the last one. I think function and thickness of oxide layers. So if on the y-axis you can see a range of thickness of oxide and the typical role it plays in the device. So if you talk about a very thin one down there, 1 nano or so it's usually chemical oxide from cleaning and native oxide. So this one at this level, at this thickness, is usually called native oxide. For example, kalau you work on silicon wafers for your whatever work, so kalau you tinggal dekat ambient or you don't encapsulate, you don't close your petri dish, your sample holder properly, so you have oxygen seeping in, and in fact you also have oxygen in the container, so it will grow native oxide over time. So the typical thickness is very low, so it's in the range of 1 or 2 nano. So it can be removed by dipping your silicon into HF for like a couple of seconds. So the changes will be, kalau you ada silicon wafer with oxide on, a very thin layer, kalau you celup dalam HF, dia akan originally be hydrophilic. Maknanya bila you angkat silicon wafer tu, dia akan jadi basah surface tu because it's hydrophilic in nature. So when do you know that your oxide is removed? Is by looking at the change on the surface. So after a couple seconds of dipping, bila you angkat silicon wafer tu, dia akan jadi hydrophobic. Dia akan jadi droplets of water of HF. Dan actually water pun sama. Bila you angkat tu, kalau you dip in the DI water, kalau dia jadi hydrophobic ataupun oxide is gone, so dia akan ada droplets, water droplets. That means native oxide is completely removed. So if you have the oxide on, it's going to be hydrophilic. If you have the oxide off, gone, it's going to be hydrophobic. So if you go for thinner oxide, so it's typically used for gate ox or tunneling ox. So gate ox for modern devices, we're talking about 3 nano or so. If you go slightly thicker, then we are talking about pad ox. We're going to see later on where do we use pad ox. So if you go for thicker than ox, then we usually use it for masking to block certain dopants during diffusion process or implantation process. If you talk about even thicker than that, then you're talking about field oxide to isolate your neighboring devices or active areas from non-active areas, or metal to metal. A couple of rows there. Yeah. So so that means if you want to use your oxide for different purposes, so you need to look into what sort of thickness range do you need for it to work. For example, kalau you nak pakai your oxide as a masking layer, tapi you pakai 10 nano, and you run diffusion process or implantation process, so it wouldn't work, okay? Because the thickness is not sufficient to block the dopants at high temperature for a long time. Or on the other hand, if you want to use thick oxide, for example, you pakai pad ox punya thickness range for your gate ox, it wouldn't work either because it's too thick. So you need to go back to the equation on how the oxide affects capacitance and so on and so forth, and the switching and the ID/VD curve in your MOSFET. So yeah, I think that's all for today. Next week we're gonna move on to the equipment and the setup and the process, and how does the thermal oxidation works in the silicon. So what does it mean by growth process instead of deposition of oxide? Right. Any questions for today? Ada soalan? All good with the intro to oxide, thermal oxidation? Ada soalan? Semua faham? Go home and check on the enhancement and depletion layers, and how does this affect your semiconductor fabrication process later on. It's going to affect the process, and at what process, to be more specific. So tak ada soalan, I assume. Yep. Then yep, that's it for today. I'll see you next week again, inshallah. So take care. Bye bye. Assalamualaikum. Have a great weekend. You too.